This is a new algorithm or new type of problem that can be solved by dynamic programming. It's called matrix chain multiplication problem. All right, so first of all, it's about matrix multiplication. So I think it can remind us of something that we talk about in divide and conquer approach, right? When we compute the matrix multiplication between two matrices, right? We said we can use the Strasson's algorithm to improve the running time from the n cube, right? From big O of n cube to big O of logarithm base 2 of 7, right? It's 2.7 something, 2 point something. So it's a slight improvement, but it's a very complex method in proposed in the Strasson's algorithm. Yeah, so in this case, we are talking about something related, but it's not exactly the same problem. It's a matrix chain multiplication problem. So there's a chain here, okay? So a chain is actually a lot of matrices, not just two matrices, okay? And it's a very good example of how dynamic programming can be applied. So I think we can lay out the background for the problem today. All right, so it is like this. Now we have a sequence of matrices, okay? And we want to multiply them up. We want to compute the products of these sequences to be multiplied, okay? We wish to compute the product A1 times A2 times AN, okay? So there are some properties we need to use here. So matrix multiplication is actually associative, which means that we can add parentheses to this sequence and the result will be the same, okay? For example, the results the 4 different ways of adding parentheses actually result in the same product. We can actually let A3 times A4 first, and then use the product to times A2, and use the product to times A1. That is the first parenthesization, okay? And the second way is different because this one, in the second case, we let A2, we compute A2 times A3 first. And the resulting matrix will be timed with A4. And the resulting matrix will be timed with A1. That is a different order of computation, okay? And you may ask why we're doing this different ordering. And actually you will see that it's quite different with have a quite different consequences. Okay, so we say that a product is fully parenthesized. So if it is either a single matrix or the product of two fully parenthesized matrix products. Let's use an example, to know why the ordering of the matrix multiplication actually matters, okay? So we need to use the rules of matrix multiplication. So if we have two matrices A and B multiplying together, we need to satisfy that they are compatible, right? So the compatible condition says that the number of columns of A must equal the number of rows in B, right? Remember this principle we use when we define the matrix multiplication. So when A is a P by Q, which is P rows and Q columns, then B must be Q rows and R columns. Only they have the matching Q here. Then we can multiply them together in order to get the product C. And the C would be P by R, okay? So the P would be the left term of A here, and R will be the right term of B. That is how we do the matrix multiplication. Okay, and actually we can use a triple for loop to do this matrix multiplication. Okay, but this is just some little review. This is the matrix multiply is not a focus of this algorithm of the matrix chain problem today. Okay, so this is just for comparison, just for review purpose, and we can basically use this to estimate how many scalar multiplication will be needed. Okay, so basically the scalar multiplication is the multiplication between two numbers. Okay, say when we want to multiply two matrices together, it's actually decomposed into a lot of steps of multiplication between numbers, and those numbers are the elements of the matrices. So in this particular case, when A looks like this, right? P by Q, B looks like this, and C looks like this. So in the computation of each element in C, actually we need to compute the products between the elements in A and the elements in B. And the question is how many scalar multiplications are needed? Because to compute a multiplication is where the heavy lift occurs, right? We need to compute this multiplication for many times. All right. So the answer is actually, the answer to this question is P times Q times R, right? So if you look at the first for loop, we have I ranges from 1 to P. The outer for loop has P iterations. The middle for loop has R iterations. And the last for loop has Q iterations. When you have 3 for loops nested and the body of the most inside for loop has 1 multiplication here, then the total number of multiplications is obviously P times Q times R, right? That is the multiplication, that is a multiplication of the ranges of these 3 for loops, right? So again, it says that the inner product, the scalar multiplications like this will be conducted for that many times. Okay, so the performance of a matrix multiplication actually is limited by this P times Q times R property. Okay. Let's assume this is the case, and let's going back to the problem of adding parentheses. Actually, different ways of parenthesization will significantly affect the running time of the matrix chain multiplication. Let's consider multiply this chain A1 times A2 times A3, right? It's the simplest chain we can get, right? It's only 3 matrices. So A1 is 10 rows, but it has 100 columns. A2 is 100 rows and 5 columns. A3 is 5 by 50. So of course we can use A1 times A2 first, and then the results will be multiplied with A3. Then let's count how many scalar multiplications will be needed if we do such an order, right? Right? When we multiply A1 with A2, the P is here, Q is here, Q is here, and R is here. If we compute P times Q times R, it will be 10 times 100 times 5, which is 5,000, right? To compute this step, it will cost us 5,000 scalar multiplications. And the resulting matrix is 10 by 5, right? We have 10 and 5 left. and 100 is eliminated. Okay, that's the first step. Then the resulting, the next step is to multiply this 10 by 5 matrix with a 5 by 50. Then the cost would be 10 by 10 times 5 times 50. That is also a new PQR, right? Which is 2,500 scalar multiplications. All right, then altogether, we will have 5,000 plus 2,500, which is 7,500. Okay, what about we do it in a different way? Like, what if we use we compute A2 times A3 first? So when we compute A2 times A3, it's actually already a lot, right? The P would be here, 100, Q would be 5, and the Q would be 5, and R would be 50. So PQR would be 100 times 5 times 50 would be already 25,000. That's already significant, a lot of much more larger than the 7,000 one, right? Not to mention we have a second step, which is to times the resulting the product between A2 and A3 with A1. That will cost 50,000 more. Altogether, it's basically 10 times larger than the first way of parenthesization. Okay, so it's actually a serious problem now. So different ways of adding parentheses, which means different ways of the order of the computation actually matters a lot. Okay, so the problem that we are interested in is that how do we find a way to parenthesize the chain of matrices in such a way that the number of scalar multiplications is minimized? Okay, so I will stop here for today and leave the solutions to the next lecture. Okay, and later today I will also release the homework for the fourth question sets that covers the dynamic programming problems. All right, any questions today? Will be due in a week, more than a week actually. I will release it today and it'll be next Friday. How many more assignments? I think there will be, so my plan is to have 8 question sets. So we are on the 4th one. So it depends. We're probably gonna have one less, which is 3 more. So including this 4th question set, we will have 4 more. Yeah, 4. Yeah,